All right. Well, thanks everyone for being here and joining us. This talk is about our efforts toward creating a graph library for the standard C++ library. Andrew Lumsdaine is joining me online. I'm Phil Ratzloff. Andrew got to do this last year. He did a presentation. And unfortunately, we didn't have a lot in the way of code to show. In that time, we've had a little more time to develop our libraries and to formalize more of what we want to do. So I think that's been a good thing. This should take most of the time. Whatever time we have at the end, we'll take the questions that we can. If you're online, I'm assuming Andrew will cover those questions as he can. If we ran out of time, I'll be in the back and we can arrange, or I can answer questions until the next meeting starts. There's also the Discord chat that you can also add to later on, and we'll try to monitor that. So I'm Phil Ratzloff. I work at SAS. I've worked with graphs for a number of years that are embedded in products related to profitability analysis and entity resolution. Andrew has worked in many areas related to high-performance computing, including systems, software libraries, and large-scale graph analytics. Open source software projects resulting from his work include BoostGraph and OpenMPI. This has been an interesting collaboration because we come at the problem in different directions. And I think overall, it's going to give us a good, broad spectrum of being able to provide a good solution. So thanks also to the others that have been involved, including Jason Feroz, Tony Leo, Kevin DeWeese, Scott McMillan, Haley Riggs, Richard Dosselman, Matthew Galati, Mohammed Osama, and those who have participated in the reviews of the proposals so far. So this presentation represents Andrew and I, and may or may not represent the views of the organizations we're associated with. So in this presentation, we'll be looking, I'll give you a little introduction to the background where we've come from and what we're hoping to do. Then we'll look at what we think of as a graph. And then I'll show you some example code of what you might be using in your project and what it would look like. And then we'll dive into the algorithms a little bit. We'll look at the views of a graph, and then the concrete CSR graph container that we are including in the proposal. Then we'll look at some other graph containers and then do some wrap-up. So this started back in 2001. I hope you can see this. When BoostGraph was released. Andrew is one of the co-authors of that. That was in the days of C++ 98 when not all the compilers, or none of the compilers, were compliant. And so their goals were to create a comprehensive graph library that would address all the needs and for all of the different kinds of algorithms that they wanted to present. And that's still a viable option today, and it's still very actively used. In the interim time, Andrew has continued to work with graphs and refine his views. And so he wanted to create something new that, taking from all of the experience and knowledge that he gained, to create a new graph. And so he started Northwest Graph in 2017 with those goals. And so in 2019, or just a little before that, the machine learning study group in the C++ standards committee decided that one of the things they'd like to see is a graph library. And so that's when I got involved and started working on the proposal. And that's also the year that Andrew and I met and decided to collaborate. And we've been discussing things and moving along in the intervening years. So at the beginning of this year, I had realized that what I had done up to that point was really learning, and so I started over with the Graph V2 library and a new approach to the proposal. Also, the Northwest Graph library was published along with a peer-reviewed paper, and there's links for that at the end of the slides. And we've also started moving the algorithms and other functionality from Northwest Graph that makes sense over the Graph V2. We're also hoping to publish the third revision of the paper at the end of this year. You can find previous revisions out there in the internet. I wouldn't waste your time on that. It has changed significantly, and I think much to the better. It's much more focused and simpler. And if we're lucky and everybody likes what they see, then hopefully, and if we do all of our work, we can get that approved by early 2025 to get into C++26. There are some caveats. It's incomplete. It's still a work in progress. Breaking changes are expected. It hasn't been reviewed outside of the machine learning study group, so there's going to be more eyes looking at it, asking for changes, and there's no guarantees if and when it will be accepted into the standard library. But so far, it's been received some very positive comments, so I'm very hopeful. So what is a graph? So let's look at what that is. So we can look at the definition saying that a graph is a set of vertices and edges, which are links between the vertices. And edges may or may not be oriented, directed or undirected, respectively. And edges may be weighted, that is, assigned a value. And I would add that vertices and the graph itself may also be assigned a value, based on my experience. So what is a graph? Well, here's an image. A lot of people, I think, would recognize this as a graph, or a network, if you will. It's just a number of routes between Germany and Germany, with the distances between. We might have the raw data to represent that like this, where we just have the distances between the cities. But the algorithms, the graph algorithms, can't work with us directly and work efficiently, so we need something else. And that something else is the adjacency list, which is an outer range of vertices, so the cities in this case, with an inner range of the routes. So we have Frankfurt going to city 1, which is Mannheim, with a distance of 85 kilometers. We can represent an edge as a route like this with a struct as a target ID and a distance, and then we have a collection of edges as a list of routes. And we can define a vertex as the set of edges and the city name. And then we have a vertices type, which is a vector of vertex, which becomes our adjacency list. And so we can fill in the rest of the routes to show the full graph. And when we render it, it looks like this. So it's really a set of one-way roads between the different cities. So in other words, you can go from Frankfurt to any other city, but you can't get back. What we really want is something like this. And so we need to augment the adjacency list, or the edges that we have, to duplicate what we had to go backwards. So in this case, we have Mannheim going to city 0, which is Frankfurt, with 85 kilometers. So the duplicates, everything's been duplicated in the pink edges. And I'll tell you, 4 years ago, I would have never created a graph like this. And the reason for this is because I have different requirements than, say, Andrew does. This is what you would do, I've learned since then. If you're going to create a graph for high performance, this is what you would do. In my world, with the embedded graphs in the products, I may have a dozen properties on an edge. So it doesn't make sense to copy it like this. So it's an easy workaround to create a separate object with all the properties and have a pointer to that from the edge. And that works, but if you want to delete edges periodically, to do that, now you have to do a linear search, in this case, Frankfurt and Mannheim, to find the edges you want to delete. And that's less than optimal. And so from my point of view, I wanted to create an edge that was a single object. Now, there's a problem here, too, in that the edge can only, if you're going to use the standard containers, you can have that edge in only one of the containers because the container owns the edge, right? So what I discovered was the Boost Intrusive library, which helped me a lot. I had a bidirectional graph where I had both incoming and outgoing lists on a vertex. And so I could embed within my edge object linked nodes for each of those lists. And it worked perfectly. It gave me the exact semantics I wanted. I could do a single allocation for the edge and its properties. And I could then delete that edge efficiently. Now, for what we're showing here, there's just a single edge list. And so that Boost Intrusive option that I had doesn't quite work for this. But I've been able to hand code my own solution that will work. And my point in all of this is that there's different ways to construct a graph or to form a graph, depending on your requirements. If you want high performance, if you want to be able to delete your edges, be able to have a large number of properties, these are all demands and priorities and goals that you may have. And these are all valid. And so for all of these solutions, what is it that we have to support in the library, in the adjacency list? And this image that we're seeing here is exactly that. It's that outer range with an inner range of edges. We can take if we look at the original raw data, we can also transform it in another way into what we call an edge list. And all it's doing is changing the city names into a city index. Some of the algorithms, this is all they need. They don't need the adjacency list, but this is a legitimate way of representing it as well. So these are the two physical data structures that are underlying the graphs. For the rest of the presentation, I'll really be focusing on the adjacency list, but we can't forget that this exists also. There are other kinds of graphs, such as bipartite and n-partite graphs, or partition graphs. I'll talk about that a little bit later. We're going to be investigating that. There's hypergraphs, where you can have 1 to n vertices on an edge, which is beyond what we want to accomplish on this. So we aren't going to be dealing with that. So in creating the library, there are a number of challenges. We need to enable high-performance algorithms and choose which ones we're going to select initially. And how to represent a container as a range of ranges. We've got 2 ranges now. So how do we continue to represent an STL separation of container, iterator, and algorithm? And then ultimately, how do we bring our own graphs into the mix so that we can use the algorithms and the views in this proposal with your graphs? How are user-defined values defined? And how to use modern C++ to make it easy and fun? Because if it isn't easy and fun, it's not going to get used. And where are the boundaries? What aren't we going to do? So hopefully we'll be able to answer these questions by the time we're done. So there's naming conventions that I've used through here. in this presentation, in the proposal, and in the code. So with the template parameters, anything that starts with a G is for our graph. Anything that starts with a V is for a vertex. Anything that starts with an E is for an edge. And in particular, we can look at, see if I can. We can look at the variable names for the vertex, like U and V. And if we look down at the edge, there's an UV edge, which is the edge between vertices U and V. So let's look at some example code of how our code that we would write when we use the library. So here's the raw data, again, looking at the Germany routes. We've got the cities and the doubled routes. We've seen why we double them now. And then we can define an adjacency list, a vector of a list of a route. And now I've created a special adapter, this RR adapter, for range of range adapter. And all it does is add a couple constructors and some customization points to enable it to be used by the library. And we'll look at those more a little later and what that means. So here's some examples of how we might traverse through the graph. So we have the vertex list view, which returns a vector or a vertex ID and a vertex range. And then once we have the vertex, we can then use the incidence view to iterate through the outgoing edges using the vertex ID. And you can see the output on the right. If we look at the Dijkstra shortest path algorithm as an example algorithm that we might use, in this case, the goal of this is to take a seed vertex and find the shortest path to all of the other vertices that are connected to it. So it takes the graph, the seed vertex, and then it returns an output, say a vector of distances from the shortest distance from a vertex to that seed, and then the predecessor, which we can use to trace back our shortest path to that seed for each vertex. So we'll start out by just using a weight function. Oh, I forgot to mention the weight function. And so we'll use the weight function of just one. It shows the number of segments. This would be useful for trains or planes, probably. Less useful for cars. But you can see how we call the function given the distance and the predecessor vectors. And you can see the output on the upper right. If we want to change to kilometers, which is going to be a little more interesting or useful for cars, we just change the weight function. And so we use the edge value function to return the kilometers for the edge. And we can see that we change the distance definition to use a double for the kilometers and just the labels. And we can then see in the upper right hand the output of this. So once we have this, now we can find the farthest city. And that's what the upper loop does. And in the lower loop, it uses that farthest ID to initialize, to walk back from Stuttgart, in this case, back through the shortest path to Frankfurt. So that gives you an idea of kind of the feel of how it would work. So once you understand that, then we can look at the Dijkstra shortest path, the real definition. This is the prototype. So it's a little intimidating to look at, so let's step through this. So we can see that it takes an adjacency list, which is a concept that we'll look at in a little bit for the graph. And then it expects to have a random access range for the vertex range. It also expects that the vertex ID is integral. And that's a requirement of this algorithm. And there's some discussion as to whether those things should be part of the adjacency list. We'll see how that one works out. And then we can see the distance, that the value types in the distance range are arithmetic, which means that they're either integral or floating point. And for our predecessor, we need to be able to assign our vertex ID to a value type of the predecessor range. And then our weight function is expecting, in the template argument, it's just expecting an edge reference. And then we have a requires statement or clause with the edge weight function concept. And we'll look at that next. And then the weight function definition is a little more complicated, just so that it returns a distance to match the distance, the value type of the distance range. So we have the edge weight function here. Again, it just takes an edge reference and returns an arithmetic type, integral or floating point. And then we can start to look at the concepts that are used to define an adjacency list. So in this case, we start with a vertex range. We say that it needs to be a forward range that needs to be sized, so there's a size function for it. And that we're expecting there to be two functions available. One that's a vertices function that takes a graph and returns a forward range. And then there's a vertex ID that takes a graph and a vertex iterator. There's the targeted edge then. So most algorithms just require a target or a target ID. And so that we're separating that from the source and source ID. And so we're just requiring that we can get a target ID or a target based on a graph and an edge reference. So with those defined, we can now define the adjacency list, which is a vertex range. It's a targeted edge, and it requires two additional functions on edges, two overloaded functions for edges. So now that we have the targeted edge, we also have a mirror on the sourced edge that requires a source ID function and a source function. And then we can define a sourced adjacency list as being an adjacency list and the sourced edge and the edge ID. Now, in terms of the algorithms for our proposal, all of the algorithms on the left are going to be in the proposal. The algorithms on the right might make it in, and it's really dependent on how long the proposal is. If it gets too long, it's going to get bogged down in the committee, and it'll be C++29 before it gets out. And I'd rather not do that. So anything that doesn't make it into the proposal will, as soon as it is making enough progress and it looks like it's going to make it in, we'll start another proposal with the additional algorithms and any other functionality we want. So then we can look at the views. We've already seen a couple of these, the vertex list and the incidents. Views are really just a way of iterating, different ways of iterating through the graph that are common for the algorithms. So let's look at those a little more closely. So the vertex list just returns an ID and a vertex. You can see what that is. And it's a little tighter when you use structured bindings, which we will continue to use. And you can also pass a value function to the vertex list, and it'll just add a third value in the return. And so you can see we're using vertex view again. There's just the bottom one is a specialization where there's a void for one of the template parameters. And so what all that means is that there's a missing member. So with that, we can also add the remaining definitions for vertex view with void for the different combinations of parameters. ID will always exist. And this can be used not only for this, but in other contexts too, that we'll see. So there's several overloads that we have. We've looked at the first two, which iterates through all of the vertices in the edge. There's some other variations based on ranges, using a range object or a pair of iterators. There's the incidence view, then that iterates over all of the outgoing edges of a vertex, returns a target ID and an edge reference. It has the, we can add a value function to add a third value. And then just for completeness, here's the edge view, the full definition of the edge view. There's a sourced template parameter which determines where the source ID exists or not. And if it does, it'll use the same type as the target ID. So we have an extra member, so there's a few more specializations defined, and you can see this. Target ID is always defined. So you should be able to see the patterns here. And so it continues on. So there's the neighbors view, which is the neighboring vertices of a vertex through the outgoing edges. So it has a target ID and a target vertex reference. We can add the value function as well, and then the full definition of the neighbors view. And again, a number of specializations with a target ID always defined. There's an edge list view as well. Now, this kind of harkens back to that edge list data structure that we saw earlier. We're emulating that by iterating through all the edges in an adjacency list. And so it's returning a source ID and a target ID and the edge reference. And we can add the value function. Then we can have the depth-first search. This is often referred to as an algorithm, but for us it's a view because all it's doing is iterating through the graph. So it's a greedy search, in this case starting at Frankfurt, and it keeps searching until it finds a city it's already found or it finds the end of a path. So there are different variations of this. There's one will stop on all of the vertices. The next one will stop on all of the edges, where the target edge is what we would get in the vertices function. And then the sourced edges, depth first search, then is the same as the edges, just adds the source ID on the return value. So with that, now it's going to get easy. If you understand that, breadth first search, I've highlighted or colored each of the cities based on the traversal order. So everything in purple is visited first, then those in pink, and then finally in orange. So here's our breadth first search functions, or the views, for the views. The exact same parameters being passed with the same type being returned. And then we can go on to the topological sort. Again, everything in purple is visited first, and then pink and orange, and then gray. Topological sort will do a search, but it won't visit a city in this case until all the incoming cities have been visited. And in this case, the only real example is München. Augsburg, Nuremberg, and Kassel have to be visited before we can visit that. And then we have the same functions with the same parameters and the same return types. So then we can look at a real graph container that we're proposing, the CSR graph. And then as part of that, we'll be looking at the graph container interface. Now, graph containers are different than what we're used to in the standard library for containers because it's a range of ranges. We've got 2 ranges, not just 1. All of the functions to access them are free functions. There's a few free functions in the standard for the existing containers like begin, end, size, and empty. But the containers also have member functions that you have to use to get access to some of the functionality. All of the functions are customization points, meaning that you can override all of the functions if you need to for your specific graph container. And then user-defined values are optional on an edge, vertex, and graph. Now, this is different than what we have in the existing containers, where if you think of map and set with a key value pair or just a key, the thing that distinguishes it is whether you have a user-defined type or not, the value type. We've done that differently. It becomes difficult to try to do that. In fact, I don't know how to try to do the same thing with a graph. So for the CSR graph container, it's a compressed sparse row. It was first designed to hold a matrix for linear algebra. It works well for us. It's high performance. It's got compact memory usage. It has a static structure, so once you've constructed the graph, you can't add any new vertices or edges. The values on the vertices and edges in the graph can change, and the values are stored separately from the structure. So here's the prototype of the CSR graph. You can see that the first 3 template parameters are for the values, the different value types for edge, vertex, and graph. There's also the integral vertex ID, and it defaults to unsigned 32-bit integer, which should work for most cases. If you have a small graph, say 100 vertices and 200 edges, you could use an unsigned 8-bit integer instead, and it will save you space by doing that. Don't go over 256. It's going to cause problems. And then there's the allocator that's used for the internal containers. And then you can see at the end how this is used to define a graph. There's a couple constructors. The first one is just for if all you have is edges. And you're passing, it requires that we pass in, it's assuming that there's an edge view, which we've seen already, which would have a source ID, target ID, and then the optional value if there's a value on the edges. And so if your E range is not a range of the edge views, then you'd have to define a projection function that would convert those values to the edge view. So then we need another constructor that would take both edge values and vertex values to add them to the graph. So what we're going to look at from here on are all of the functions and the types and the traits and concepts that we would have for a graph container. But it's not only for CSR graph, it would be for all graphs. And this is the API, if you will, that we're exposing that's going to be used by the views and the algorithms to do their work. So here's the functions for the graph and the vertices. These are all customization points, so they can be overridden for a specific graph container type. So there's default implementations for many of them that you can see on the right. If you look at the vertices function, there's an NA, which means that it has to be overridden for a specific graph container type. If you look at the graph value and vertex value, it's NA and optional. That means if the graph doesn't store vertices or store values on the vertices, you wouldn't have to override it. It wouldn't be available. So there's the edges functions. We've seen a number of these already. The same idea, there's the default values on the right. There's the find functions and the contains functions, which are all linear. All of the rest are constant time. And then there's a sourced edge function. So if we have a source ID on an edge and the source ID function is overridden, then the other two functions would be available also. And this just mirrors what we were showing in the concepts earlier. So if we have then we have the different type aliases defined for graph and vertex. We've seen some of these. They're either defined as the return type of a function or a refinement of an existing type. So like the vertex iterator is an iterator of the vertex range. So we have the edge type, the type aliases for the edges, and the different definitions as well. So there's a number of traits that determine whether a function is available that an algorithm could use to assure that it can perform its work properly. For degree, for the find vertex edge, and contains edge. There's also an unordered edge and ordered edge trait. Now, in this case, remember back when I was saying that we may have some edges where we just want a single object. It would have a source ID and a target ID on it. And we have a single edge list for the vertices. Well, the target ID would be correct for one of those vertices, but it would be incorrect for the other one. It would have to be reversed. The source ID would really be the target ID. And so we can tag or we can specialize this for a graph container type to say that we have that situation. And the views will use this to do an additional check to make sure it's returning the proper target ID or source ID. There's also an adjacency matrix trait. The define adjacency matrix can be specialized for a graph container type to say that it's an adjacency matrix. And all that means typically is that the edge values are stored in a two-dimensional array. And some algorithms can take advantage of that. As far as the concepts, we've already seen the concepts we have so far. We may add some more later. That's what we have. So there's some other graph containers. Certainly our graph containers that we would bring to the party. And then there's a few others that are part of our project I'll tell you about. So if we're going to integrate an external graph, there's the three functions on the left that have to be overridden: the vertices, edges, and target ID. The value functions would be over on the right. Everything on the right is optional. For the value functions, if the graph has a vertex value, you would override that. If it has an edge value, you would override it. Otherwise, you wouldn't have to do anything. For the vertex ID function, that's what defines what the vertex ID type is, whatever it returns. Normally, in a 64-bit system, it would return a signed 64-bit integer. And it's the difference type for an iterator. So if you want it to be like an unsigned 32-bit integer, you would have to override that to return a value of that type. So this uses, I'm not sure how much customization points are understood yet. There's a couple ways of implementing them. The first, used by the standard today, is called a nibloid. And the thing to focus on here is really the function signature. So in this case, there's the vertices that takes the RR adapter graph. And it just returns then the whatever the vertices function returns on that graph. And there's a const and non-const version. The other way of doing this is a tag invoke. And this is, I think, as I understand it, it's being discussed as whether this is a valid technique to use or not within the standard. And you can see here that the function signature is a tag invoke function. And the first parameter is a tag, if you will, a special type that indicates what function you want to do. And all it does is it reduces the number of names in the namespace. This is what I use because it's simple, it may get changed, but it gives you an idea of how you would use this with your own graph. We're also looking at a thing called a CSR partite graph. This is just a working idea that we want to look into. The class prototype is identical to the CSR graph, except that what we want to do, we'd be using variants for the edge and value types. A partite graph is partition graph, and what that means is that there's n partitions, where each partition we can have a different type for the edge and the vertex. So in this case, we can see that the variants being used are defining three partitions because there's three elements in the variant. And so partition 0 would have a double for the edge value and an int for the vertex value. That's the first element types. And we'd also need to add some additional functions, probably more, to support this. And this is going to be important to look at because I think it's going to change the graph container interface. And so we want to get that in place. I don't expect this to go in the initial proposal, but we want to get everything in place so that we can do a second proposal to include this. So there's the RR adapter, or I should say, Andrew would be happy if I told you that the importance of having a partition graph is for labeled property graphs. And there's a number of algorithms that are specific for this type of thing. The RR adapter is something that we saw a little earlier. It's just part of the demo that I'm showing today. I think we'd like to get something like this available for, along with the other graph containers to make it easy to create a solution, or to create a graph. Another thing that I did earlier on, just for my testing purposes, that may or may not be useful, is this dynamic graph. It has a sourced template parameter which tells that that we're going to have a source ID on the edge or not. And then there's the traits parameter. And here's an example of that. And what it allows me to do is to quickly change the container that's used for the vertices and also for the edges. And so in this case, we've got the vector and forward list. So for the vertices now, I can use a vector and or a deck. They both have, it has to be a random access today. I think it'd be interesting to throw in a map also, just to see if I can make it work. And that can be useful if you have sparse vertex IDs. We're not going to support that in the standard, or at least in our proposal. So, but I don't want to give anybody the wrong idea here, but I think it would help to prove the existing design so that it's extensible for the future, either inside or outside the standard. The edges type could be a forward list, a list, deck, or vector. Boost Graph had something similar, similar capabilities by using tags that were predefined, but this is a little more straightforward in its definition. And it should be able to adapt to other containers outside the standard. All right. So as far as the timeline goes, we were hoping to have the next revision for the proposal by the end of this month or end of the year, and hopefully have it be accepted by the machine learning study group so that it can move on to the other groups. A requirement, I think, is going to have the matching implementation to go with the proposal, so people can kick the tires. Eventually, the target date that we have is February of 2025 to have it accepted by everybody and to be accepted for C++ 26. So far, the response has been pretty positive. So I'm look forward to see how this goes. Final comments. The parallel algorithms aren't being addressed yet. A lot of the algorithms, a lot of graph algorithms don't lend themselves to parallel implementations. There's also some work being done to figure out a higher level of parallelism with the execution. There's an execution proposal, I think, P2300. And so we want to get focused on just providing the basics right now. And once that has matured and been accepted, and once we've got this further along, we can address the parallel implementations. If you happen to look at this, your input is welcome. This week, I'm going to be around. I'd love to hear from you. If you happen to use it and have some experience with it, I'd love to hear about that. If you want to use it, you might want to wait until the end of the year, until it's gotten a little more mature. And then, of course, start the GitHub once you look at it to help us out. So to find out more, here's the links to the code and to the paper. The paper itself, the link for the paper isn't going to work because it hasn't been published yet. But once it's published, you'll be able to follow that and find the proposal by the end of the year. Before that, you'll find the LaTeX paper that you can use or look at. Northwest Graph, the library and the paper is also available for you to review. And then last year's proposal presentation by Andrew is also available. And you're always welcome to contact us by email as well. All right. So it looks like we have 10 minutes for questions, which is 5 more minutes than I expected.
Is pointer stability any part of your interface, or like,
Pardon?
are you offering pointer stability for your interface, or
In which part?
like when you have, do you have any dynamic ability to add to the graph, or they're all like static size?
Well, for the CSR graph, that's static.
Yeah.
And so we don't have to worry about that.
Yeah.
So we dodged that bullet.
Yeah.
But I think that would apply more to the other concrete graph containers that might come along.
Okay, so if you have some, well, the dynamic graph was dynamic in which sense? Was it, you could add edges and vertices dynamically, or?
Edges, yes, for sure.
Okay.
For vertices, if you use a deck, you could probably get for the that stability that you want.
Okay, thank you.
Okay, so you said that you don't do parallelism with the algorithms yet, right?
Correct.
But the data structures themselves, right, would be something one could try and use in parallel contexts. Did you do that? Did you check, in particular for things like CSR graph, if you use it to implement like sparse metrics, vector multiplier, which is something we could compare to vendor libraries, and how does that perform if you did?
Very good question. Once it gets out of the machine learning group, I think other groups will be looking at that, and we'll be able to look at that more in detail.
May I make a comment about that as well?
Yeah, that's Andrew.
So in the NW graph library that Phil mentioned, well, I guess it's on this last slide, we did do a lot of parallelization of different algorithms in the NW graph library. As Phil mentioned, there is some difficulty in that, sometimes the parallel algorithm that you would use to solve a certain graph problem is not necessarily a parallelization of the algorithm that you would use to solve that problem sequentially. So Dijkstra's algorithm is a perfect example. The algorithm itself is inherently sequential, so one can't just parallelize pieces of it using standard library parallelization to get a parallel algorithm. Rather, you have to use an algorithm like delta stepping to solve the problem that Dijkstra solves. That being said, there are other algorithms, as you mentioned, like sparse matrix vector product that are amenable to parallelization. So in NW graph, we did use STL, or standard library execution policies in some cases to speed things up. But one other thing we found out doing that, though, is that there are some limits to what the standard execution policies can do for speeding up. In particular, as Phil mentioned, graphs are a range of ranges. The standard library parallelization will just partition the outer range into equal-sized pieces, which is very likely not going to represent equal amounts of work due to the different sizes of the inner ranges. So what we had to do in NW graph actually was use TBB, Intel's threading building blocks, so that we could manually, or based on the algorithm and the graph structure, control how the parallelization was done. So that's really something that, so the short answer to your question is some algorithms can be parallelized with the standard library parallelization, but actually not very many. And we need a richer mechanism for doing parallelization that could be under the programmer's control to really apply that to
just to clarify, right?
Containers in the graph algorithms.
Mostly I'm concerned about the appropriateness of the data structures themselves for writing your own parallel algorithms, around them, right? Using them inside of, OpenMP, CUDA, whatever, right? Independent of the parallelization of the proposed algorithms themselves.
Well, again, it depends on exactly which data structure you use. So the algorithms we were talking about are generic, so don't necessarily depend on any particular data structure. But that also being said, the CSR we found in NW graph is perfectly suitable to doing multiple different types of parallelization. And we used it for parallel, well, that was the primary data structure we used in NWGraph for doing the parallelization, even with the TDB mechanisms.
So this is on like a similar note with the performance. So this is not about parallelization, but I was wondering, so the traits you mentioned, that was an interesting idea. Are there any considerations, for example, when you construct like a CSR on the topology of the graph? Because I'm not sure if you have any, room for algorithms like vertex reordering and things like that to even like further extract, performance for these types of special graphs. Are there currently any considerations for these types of algorithms?
Do you want to take that, Andrew?
Sure. Well, again, kind of reflecting to some of the experiences we had in NWGraph. So, for instance, in triangle counting is one algorithm where doing vertex ordering according to vertex degree makes a huge difference in the performance of the algorithm. So those are some component pieces that we've been considering for standardization. One thing, kind of corresponding to that and is necessary in certain algorithms such as triangle counting is you want to make sure, say that within a neighborhood, within one of the inner ranges, or the range of ranges, you want the neighbors to be in sorted order. Because the algorithm, for instance, does set intersections.
Yeah, I think for certain like domain-specific applications, might be, for example, like a scale-free graph. If you implement it in memory in some ways, you would get more of a performance benefit. But I think it will be very exciting to let the developers have customizability, using this sort of standard container as you've shown. But yeah, thanks for the tremendous work.
First of all, thanks for the presentation. So I have two implementational details questions. First is, you guys said that the graph is going to be range of ranges. So I just want to understand what is the outer range and what is the inner range. I imagine it's going to be the vertex and the edges, but like how it's going to be arranged. And my second question is, as we are dealing with the iterators in this, how we are managing exceptions and where.
Well, the outer range and inner range is the adjacency list that we were looking at early on. So yeah, the outer ranges are the vertices, and the inner ranges are the edges on the vertex, on a vertex.
And how we are managing the exceptions as we are dealing with the iterators use?
There's nothing special that we're doing for exceptions, so any exception that might occur would just be thrown normally.
Okay, cool. Thank you.
Given your use of concepts, what benefits do you expect from using nibloids?
Well, nibloids give us the opportunity to override the functions for a specific graph container.
Yes.
Can you offer a different way of doing it? That's the only way that I know how to do customization points.
Okay.
Hi, thank you for the presentation. I had a question regarding the deepest or shortest path. Would this framework or library be extensible to different heuristic methods? Like, how much of a leap would it be to do a star from what's been shown?
Andrew?
No, that's a really good question. And Phil alluded in a couple of places to the original Boostgraph library. And there, We tried to really layer a lot of the algorithms on top of each other so that we could do that kind of extensibility. In some sense, it was successful in that within the library, we could achieve that kind of reuse and extensibility and layering. But some of the mechanisms that were put in place to make that happen ended up, I think, making things a little too abstract and too generalized, and kind of work, to use a phrase that's often heard, became very expert friendly. And so we're trying to balance those two concerns. So some of this will also depend on, as we're moving the proposal forward, what kinds of algorithms are considered to be useful and where we might draw the line as far as what this library would actually provide versus what other algorithms are people really think are important, and how extensible then do we need to make the provided algorithms to support the kind of extensions you're talking about.
Thank you.
Okay, I understand that we're done. So I'll hang out in the back. It's just going to have to be me. But I'd be happy to answer any questions until we're kicked out.